All right, folks, continuing on here in Chapter 3. You're going to really like Section 3.3 because we start to introduce some rules, or shortcuts, if you will, of differentiation. All right, so, let's be honest. Computing derivatives using the definition of the derivative, it can be cumbersome and tedious. Thankfully, that definition of the derivative is the mechanism that gives us some rules, or shortcuts if you prefer, for computing derivatives. Every rule we will learn is proven to be true by using the definition of the derivative. And even going ahead, I'm thinking ahead, there will be occasions when we have to appeal back to the definition of the derivative in creating some rules. And we kind of have to do that. And it's almost like, in my mind, I use it, as a last resort because the definition of the derivative is cumbersome and tedious. In this section, we're going to learn 4 rules for computing derivatives. And our first rule, which I will give the name the constant rule, it tells us the derivative of any constant. So here it is. Here's your first rule or shortcut on computing derivatives, the constant rule. The constant rule says if c is a real number, then the derivative with respect to x of c is 0. That is, if your function f of x equals c, then f prime of x equals 0. In English, this rule simply states the derivative of a constant is 0. It's probably the friendliest rule we could have. So here's our first example. Determine derivatives for part A, f of x equals 7. Part B, f of x equals negative 13. Part C, f of x equals pi squared. I'm not even going to the chalkboard for this one. In part A, since 7 is a constant, the derivative, f prime of x, is 0. Part B, f of x is negative 13. That's a constant. So f prime of x is 0. In part C, pi is a constant. That means pi squared is also a constant. So the derivative is 0. Now you probably hope you'd like to see about 8 of these on your first test. Well, you're not going to, but it would be nice to see that many. But you do need to remember the derivative of a constant is 0. All right, so let's look at our next rule. So to see where the next rule comes from, I'm going to ask you to consider the following, and let's look for a pattern. In each of these that I'm going to write down, the derivative of the function, well, it can be found by using the definition of the derivative. So here's the first one. Function is x squared. I can use the definition of the derivative to compute that for the function f of x equals x squared, the derivative is 2x. Let's look at the function x to the 5th. I can use the definition of the derivative. I don't want to, but I could use the definition of the derivative. I'm not really excited about taking an x plus h and raising it to the 5th power. That's what I would have to do if I used the definition of the derivative. But I could use the definition of the derivative to determine that the derivative of x to the 5th is 5x to the 4th. If my function is x to the 6th, I could use the definition of the derivative and probably about 3 or 4 pieces of paper to determine that the derivative is 6x to the 5th. Now, I don't know about you folks, but I'm detecting a pattern here for the function and what its derivative is. The pattern I seem to be detecting is that to get the derivative, the power or the exponent comes out front, and then we subtract 1 from the exponent. Look at x to the 6th. the derivative is 6x to the fifth. It looks like the exponent of 6 came out front, and then we subtracted 1 from the exponent. That's also true for the function x to the fifth. And folks, that is exactly what the power rule states. So let's look at the power rule. That's our next big rule or shortcut for computing derivatives. And I'm calling this theorem the power rule. So the power rule states if n is a rational number, then the function f of x equals x to the n. That function is differentiable, and the derivative is f prime of x equals n times x to the n minus 1. I could have written that down as d dx of x to the n equals n times x to the n minus 1, because just reviewing that notation, the d dx notation, that just means the derivative with respect to x of x to the n is n times x to the n minus 1. I have a special note on the power rule that when n is equal to 1, your function f of x, it's just simply x, and the derivative of x is 1. So let's practice this power rule. I have 4 of them here. In part A, we're going to differentiate f of x equals x cubed. Part B, f of x equals square root x. Part C, f of x equals 1 over x cubed. And part D, f of x equals pi to the fifth. So get these written down because I'm going to head off to the chalkboard to do them. And in parts B and C, we will review some important algebra that makes the calculus much easier to do. So here I go off to the chalkboard. Hey folks, in this example we were asked to differentiate 4 different functions, parts A through D. Differentiation is looking a lot more friendly now that we're having some shortcuts. Some of these rules that allow us to compute derivatives just like that. So in part A, the function is f of x equals x cubed. The power rule tells us immediately the derivative is 3x squared. That's it. Part B, the function is square root of x. Now I have to do a little bit of algebra first before I can do any calculus. Here's the algebra. Rewrite square root x as x to the 1/2. Folks, remember in algebra there was this rule, I'll write the rule up here, that the nth root of x can be rewritten as x to the 1 over n. That makes the calculus so much easier. Look, power rule gives us the derivative is 1/2 x. Subtract 1 from the exponent, you get negative 1/2. Or if you wanted to simplify this down, it would be 1 over 2 square root x. Part C. Get the derivative of f of x equals 1 over x cubed. I have to use a rule of exponents that I used in part B, but this rule of exponents said if you have x to the negative n, you can rewrite that as 1 over x to the n, provided of course x is not 0. So I need to use this old rule of exponents going in this direction. I need to rewrite 1 over x cubed with a negative exponent. I need to rewrite 1 over x cubed as x to the negative third. Then the power rule immediately gives me the derivative, negative 3x to the negative fourth. Or if you wanted to get rid of that negative exponent, it would be negative 3 over x to the fourth. Notice I kind of used that rule, that old rule of exponents, and going from here to here. X to the negative 1/2 would come to the denominator and be x to the positive 1/2. And then I could rewrite x to the 1/2 as square root of x. Part D, the function f of x equals pi to the fifth. Go ahead, write down what you think the derivative is. I'll give you a few seconds. All right, if you said the derivative is 5 pi to the fourth, you are wrong. Pi is a constant. Pi to the fifth power is a constant. So the derivative is 0. The derivative of a constant is 0. So didn't mean to trick you there. I just want to keep you on your toes to make sure you recognize constants. Power rule. Kind of looking friendly. Let's head back to the slides and see what the next rule will be. All right, folks, power rule is a pretty friendly rule. So let's continue on and see what our next rule is. Our next rule shows us how we can differentiate a constant times a function. For that reason, this next rule is called the constant multiple rule. And for this theorem, that's what I name it, the constant multiple rule. So in this theorem, f is just a differentiable function. C is a real number. So the product C times f, so the real number times the function, that product is differentiable, and the derivative with respect to x of the constant times f of x equals just simply that constant C times the derivative with respect to x of f of x, which is nothing more than C times f prime of x. Now, informally, we can think that that constant, that C, is factored out, or maybe it's better to say it passes through the differentiation process. And, one quick fact, you could take the power rule and you can combine it with the constant multiple rule, and it would look something like this. When you differentiate a constant times x to the n, well, that's a constant times the derivative of x to the n, and the power rule tells us the derivative of x to the n is n x to the n minus 1. So the combination is just simply c times n x to the n minus 1. So you know what we're going to do now? We're going to do an example where we practice using this new rule. So let's differentiate the following. Got 4 of them here. Part A, we're going to compute the derivative of y equals 3 over x. Part B, we're going to differentiate f of x equals 4x cubed. Part C, we're going to differentiate f of x equals negative 5x cubed over 2. And then in part D, we'll differentiate y equals 5 over 3x to the fourth. So get this written down, folks, because I'm heading off to the chalkboard to compute some derivatives. All right, this example, new rule, more practice, using shortcuts, using rules to compute derivatives. Makes life a lot easier. Part A, we were given the function y equals 3 over x. My first step would be to rewrite the function as 3x to the negative first. Okay, so now for the derivative. So if I were seeing you face to face live, I would say, what do you want to call the derivative? Do you want to call the derivative y prime or dy dx? Doesn't matter which. If you said y prime, I would write down dy dx. If you said dy dx, I would write down y prime. I need you to know y prime and dy dx are interchangeable. That's going to be really important in a future section. So I don't care what you call the derivative here. So if you're saying y prime, call it y prime. I'm going to write it down as dy dx. Negative 1 comes out front. So I'm combining the constant multiple rule with the power rule. So 3 times negative 1 is negative 3. Subtract 1 from the exponent. Exponent's negative 2. Or negative 3 over x squared. Part B, f of x equals 4x cubed. F prime is, well, Constant multiple rule. Bring the 3 out front. 4 times 3, 12. Subtract 1 from the exponent. Boom. Done. Piece of cake. C and D. I want you to pause the video, and I want you to do parts C and D. After you've done C and D, restart the video, and I'll be here at the board. We'll make sure you have the correct answer. All right, folks, part C. I'm going to rewrite the function. That's how I am on these. Negative 5x cubed over 2. I'm going to rewrite it as a negative 5 halves times x cubed. And now I'll use the constant multiple rule. 3 comes out front, gives me a negative 15 halves x squared. Or you might have had negative 15x squared over 2. It's the same thing. Part D. Okay, I would rewrite the function as 5/3 x to the negative 4th. And then I would ask you, what do you want to call the derivative? Y prime or dy dx? So if you said dy dx, I would write down y prime. So that's what I'm going to do. Derivative, y prime. Negative 4 comes out front, gives us a negative 20/3 x. Subtract 1 from the exponent, negative 5. Or if you want, I suppose you could write it as negative 20 over 3 x to the 5th. And that's it for that example. So let's head back to the slides and see what's in store for us next. All right, I hope that example was making sense, and I hope that when I turned you loose on parts C and D to do yourself, I hope you were able to do them. Let's continue on for our final rule of this section. The final rule addresses, well, how do we differentiate, or how do we handle a function that's comprised of multiple terms? I mean, if you notice, so far everything we've looked at has just been a single term. So what if we have 2 or more differentiable functions that are being added together or being subtracted? Well, our final rule is called the sum/difference rule, and it tells us exactly how we can do this. So the sum-difference rule, it starts off by saying the sum, and or difference of 2 or more differentiable functions is differentiable. And when you differentiate with respect to x, f of x plus or minus g of x, and there could be more functions in there being added and subtracted, that's equal to the derivative with respect to x of f of x plus or minus the derivative with respect to x of g of x, or it's f prime of x plus g prime of x. So really what this is saying is the sum-difference rule saying if you have 2 or more differentiable functions being added or subtracted and you want to get the derivative, you just do term-by-term differentiation. That's it. So let's practice this. Let's get derivatives for the following. So you can write these down. Please get them written down. Get them in your notes. Because I'm going to head off to the chalkboard and do them. All right, now that we've learned the sum and difference rule, we can really expand the types of functions we can quickly compute derivatives for. In this example, part A, differentiate f of x equals 2x cubed minus x squared plus 3x minus 1 over x squared. My first step is algebra. My first step is to rewrite the last term as x to the negative 2nd. So then, the calculus with the sum and difference rule, we can just do term-by-term differentiation. So the derivative of 2x cubed, well, that's 6x squared, minus the derivative of the derivative of x squared is 2x, plus the derivative of 3x Well, that's 3. And then the derivative of x to the negative second. So the negative 2 comes out front, so we'd have minus negative. So that's plus 2x to the negative third. That's as far as I'm going to go on that. Part B, g of x equals pi to the fourth plus 3 pi squared. Think about it for a few seconds. All right, hopefully not too many of you said the derivative is 4 pi cubed plus 6 pi. Pi is a constant, so pi to the fourth is a constant. Pi squared times 3 is a constant. A constant plus a constant is a constant, so the derivative is 0. Okay, hopefully most of you got that. So here's a few I'd like you to practice right now from the section 3.3 exercises. Number 26, 32, 36, and 48. So that's 4 of them I'd like you to do right now. So pause the video, do those 4 from section 3.3 exercises. Once you're done with them, restart the video and I'll be here at the board to work through them. Hey folks, in number 26 you were given the function f of v equals v to the 100th plus v plus 10. You're asked to get to the derivative. Very quickly, you should have gotten the derivative to be 100v to the 99th plus 1. Boom, done. In 32, you were given f of x equals 6x to the 5th minus 5 halves x squared plus x plus 5. So the derivative is, see the 5 comes out front, so we get 30x, subtract 1, so 30x to the 4th, minus 2 comes out front, so 5 halves times 2 is 5x to the 1st, and then the derivative of x is 1. Well, the derivative of the constant is 0. So that's it. That's the derivative for 32. 36. We were going to have an s of t equals 4 square root t minus 1/4 t to the 4th plus t plus 1. So I start off with just a little bit of algebra. Rewrite the square root of t as t to the 1/2 power. And that'll make the calculus much easier. So s prime of t, see the 1/2 comes out front, 4 times 1/2 is 2, t to the negative 1/2 minus, well, 1/4 times 4 is 1, so it's minus t to the 3rd power plus 1. And I'm going to stop there. And then at 48, I believe your book had all of these as s's. That were way too many s's for me. I was getting confused. My s's started to look like 5s. I just turned them into x's. It's not going to change the process. Well, here, I think my first step is a little bit of algebra. Keep in mind the denominator is a single term. That means I can rewrite this mess as 3 separate fractions. It's like the meaning of a common denominator. And then I can simplify each fraction. 12x cubed over 4x. That simplifies to a 3x squared. 8x squared over 4x. That simplifies to a 2x. And then 12x over 4x simplifies to 3. So now it should be very friendly to get the derivative. I don't know, what'd you call the derivative? Y prime or dy dx? I don't know. I'm going to call it dy dx. And I get 6x minus 2. So hopefully you got those 4. We're going to head back to the slides and see what's coming up. All right, we just saw how to use the sum and difference rule. Notice it also involved other rules as we were doing it. I gave you 4 problems to practice from the exercise set. Hopefully you got those. Hopefully you're saying, wow, it's so much nicer now computing derivatives now that I have these shortcut rules. Let's check out this example. So we're kind of looking at starting to introduce maybe a little physics. This is a pretty benign example. You have the position of a small rocket. It's launched vertically upward, and its position is given by s of t equals negative 5t squared plus a 40t plus 100. Here, t is between 0 and 10. T is measured in seconds. S is measured in meters above the ground. Part A, we're going to find the rate of change in the position, that's instantaneous velocity, of the rocket on the interval 0 to 10. And then in part B, we're just going to determine at what time is the instantaneous velocity 0. So folks, get this example written down because I'm going to head off to the chalkboard and work through it. Okay, in this example, there were some words. It said a position of a rocket. It's given by this function. T is in seconds and S is in meters above the ground. Part A, find the rate of change in position, and that's instantaneous velocity, on the interval 0 to 10. And then in part B, at what time is the instantaneous velocity 0? So in general, in physics, a position function can be represented by s of t. T represents time. Then the velocity function, it's given by v of t, and the velocity function is nothing more than the derivative of the position function. So for this one, in part A, when you're asked to find the instantaneous velocity of the rocket on the interval 0 to 10, it's basically just saying get the derivative of the position function. So the velocity function is the derivative of the position function, and that would give us, let's see, a negative 10t plus 40. Then folks, in part B, it says at what time is the instantaneous velocity 0? So at what time does velocity equal 0? Well, just take the velocity function, set it equal to 0, and solve for t. And if you do that, you get t is 4, be 4 seconds. So that's it for this example. Let's head back to the slides and see what's next. All right. Our final topic in this section is something called higher order derivatives. Okay, that sounds kind of imposing, but it's not. Higher order derivatives are nothing more than derivatives of derivatives. So for example, we know f prime of x. Well, that's also known as the first derivative. F double prime of x, and I gave notation, d squared f over dx squared, alternate notation. That's called the second derivative. The second derivative is nothing more than the derivative of the first derivative. This, I would read it as f triple prime of x, or f, and then it's like a square bracket with a 3 inside of it, of x. I would read that as just the third derivative. So the third derivative is nothing more than the derivative of the second derivative. And et cetera, et cetera. We could do a fourth derivative, fifth derivative. Let's just practice this. Let's determine the third derivative for the following. Now, keep in mind, we can't determine the first derivative until we know the second derivative. And we can't get the second derivative until we know the first derivative. So for this example, we're going to have to determine the first, second, and third derivatives in order to answer the question of just get the third derivative. And here are the functions. So at this time, you're hopefully really dialed into the process of how I do things. You need to have this example written down in your notes because I am heading off to the chalkboard to work through it. All right, we just took a brief look at higher order derivatives. Keep in mind a higher order derivative, it just means derivative of a derivative. So for this example, it was like find the third derivative for each of these functions. Well, to get the third derivative for f of x equals 7x cubed plus 2x minus 15, we can't just immediately get the third derivative, we have to build up to it. So we have to first compute the first derivative. Well, the derivative of this function is 21x squared plus 2. Once we have the derivative, we can get the second derivative. The second derivative is just the derivative of the first derivative. So the second derivative is 42x. Now we can get the third derivative. The third derivative is the derivative of the second derivative. So the third derivative, the derivative of this is 42. So part B, y equals 6x plus 5x to the 8th. We're supposed to get the third derivative. So we start off, we have to get the first derivative, which is 6 plus 40x to the 7th. That comes out front, subtract 1 from the exponent. Then the second derivative, that's the derivative of the first derivative. See, that's, well, that would be 0. 40 times 7, so that's 280 x to the 6th. And now the third derivative, which is the derivative of the second derivative. 6 comes out front, so 280 times 6, that's 1680, I believe, x to the 5th. Doing higher order derivatives, piece of cake. There's one more problem I'd like you to do. It's not related to higher order derivatives, but it's just kind of a conceptual problem. So I would like you now to try in section 3.3 exercises number 60. So pause the video, do number 60. Once you're done with it, turn the video back on. I'll be up here working through it to make sure you have it correct. All right, folks, so number 60, you were given f of t equals t cubed minus 27t plus 5. And in part A, you were asked to find the values of t or the slope of y equals f of t, or the slope of the function, where it is 0. So folks, remember, slope, derivative. So we need to get the derivative. We need to get the derivative of the function. So the derivative of the function is 3t squared minus 27. And we want to know where the slope of y equals f of t equals 0. That's like slope of the tangent line is 0. So since the derivative gives us the slope of the tangent line, we want to know where this is 0. We just take it and set it equal to 0 and solve for t. So add 27 to both sides of the equation. Divide both sides of the equation by 3. Take the square root of both sides. Remember the plus or minus when you take the square root to insert the plus or minus. So there are two values of t where the slope of this curve would be 0, where we would have a horizontal tangent line. So in part B, find the values of t where the slope of y equals f of t is 21. Find the values of t where the slope to the graph, or with the tangent line slope to the graph of y equals f of t is 21. Means the same thing. Part B, we just have to take the derivative. We already know the derivative. We want to know where the derivative is 21. We want to know where the derivative equals 21. So we'd add 27 to both sides. Divide both sides of the equation by 3. So that gives me 16. Take the square root of both sides. We get two values of t, plus or minus 4. So hopefully you got those, thought about them, and you were able to process it. In any event, that's it for section 3.3. So you can now do all the exercises listed for section 3.3. So do the 3.3 exercises, and thanks for watching.